Hey guys, how you doing? This is Coach Scott, and this is Unit 1B video, or the video for 1B. We're going to be talking about electrons and protons today. So, in the late 1800s, scientists were passing electricity through glass tubes that contained a small amount of gas, things like oxygen. And when the power was turned off, the tube emitted light and glowed. Okay, so like an electric light, right? So when the power was on, you had a nice glow to it. And if you look down here, you can see this nice little, this is a little picture of a cathode ray tube, but they'd have a nice green glow through there, right? So the positive electrode, we call that the anode, and the negative electrode, we call that the cathode. So we call these rays cathode rays because they appear to be coming from the negative end of the tube. So you saw this phenomenon and folks were like, what are these rays, right? Or what are these cathode rays? So when they passed an object, or when they placed an object in the path of the rays would cast shadows of the objects that were placed in their path, right? So, just like in this one, oops, all right, the cathode ray would come through, and let's say they had a metal cross on the anode. There would be a shadow of the metal cross would be at the end of the tube, which is sort of cool, right? So, it could be light, or it could be a stream of tiny particles. So, scientists found that they could deflect the beam by putting it around another electrical field around it, right? So why would the beam deflect toward the positive plate? And would this mean that the rays, or light rays, are particles? So let's think about that. All right, so the beam would go toward the positive plate because it carries a negative charge. And would this suggest that it would be a light wave or a particle? It would be a particle, right? Because light waves would not be deflected by an electrical field. Now, they also found that they could deflect the beam by subjecting it to a magnetic field. So the ray would go toward the magnetic field, right? And would this make it suggest that it's a light ray or a particle? Well, in physics, there's something called the right-hand rule. So in a magnetic field, the negative charge would deflect up. And this again suggests that it is a particle, because light waves would not be deflected by an electrical magnetic field or an electrical field, right? So scientists determined that a very weak electrical field could deflect the beam a great deal. So, if the particles are really easy to deflect, they either have a small watt or a very large watt, or both. Let's think about it. That would mean they must have a really small mass. Why? Because small things are easier to move than big things. Or a large charge, which would suggest that opposites attract. Or maybe it was both, right? So, a scientist called J.J. Thomson, he was able to determine that the charge to mass ratio would be 1.76 times 10 to the 11th coulombs of charge per kilogram of mass. All right? Now, at this point, they knew the charge or the mass of this particle. Just that they had a ratio was large that would indicate either a large charge or a small mass. Now, what was interesting was that these negatively charged particles were found in all gases, hydrogen, oxygen, what have you, that they experimented on, and they all had the same charge to mass ratio. They saw a trend, okay? They saw a pattern. They all had the same charge to mass ratio. So this would suggest what? These physicists proposed that these negatively charged particles that they would be called electrons. And because they have the same charge to mass ratio as the negative particles generated by static electricity, heated materials, and illuminated materials. Right? So, let's take a thought question here. What characteristic about the cathode rays led them to believe that they were negatively charged? Take a second. Pause. And here we go. Well, B and C. Their behavior in the electric field and also their behavior in a magnetic field. Another thought question. Which of the following indicated the cathode rays had a large charge to mass ratio? They caused the screen to glow? No. They were deflected toward the positive electrode? They were deflected toward a negative electrode? Or I need help? Well, it's because they were easily deflected, okay, by both of those fields, both the magnetic and the electrical field. So another experiment, a scientist named Millikan, he would squirt oil drops into a box, and then he passed high energy X-rays at the box. And what he was trying to do was to knock some electrons off the air molecules and onto the oil drops. And this is a model of his experiment. So he would put this ionizing radiation, X-rays. He would pass that through this little thing, and then he would look, right? And then he would spray some oil as it went down. And then these were charged plates. This is the anode, this is the cathode, right? The positive and the negative. And he was able to measure how much energy was necessary to stop the drops from falling down, and they would just hang there, right? So he was able by this to determine the charge per drop. The more energy needed to prevent the drop from falling, the smaller the charge of the drop. Okay? So here's some data, right? So one drop would have a 4.8 times 10 to the minus 19th charge. The other one would have a 3.2 times 10 to the minus 19th charge. Then 6.4 times 10 to the minus 19th, 3 drops. And then the fourth drop was 9.6 times 10 to the minus 19th. So you might see a pattern there, right? Okay, he found that the charges on each drop were a multiple of a number. All right, for just a second, let's see if you can see that pattern. When he saw that, he was able to predict what the charge of an electron was. And he interpreted it that this was the charge of an electron. Now let's think. 3.2 doesn't go into 4.8. So what number would go into every one of those one of those numbers? Well, let's see. 8 would go into 3.2. Going to 48, going to 64, smallest number. If you took 1.6 or 16, those would go into each of those numbers. So he was able to determine that what the charge of the electron was. And he correctly stated that the charge of the electron was 1.6 times 10 to the minus 19th coulombs. So that's the charge of an electron. So let's think. If the charge of an electron is 1.6 times 10 to the minus 19th, and the charge to mass ratio is 1.76 times 10 to the minus 10 to the 11th coulombs per kilogram, what is the mass of an electron? 1.6 times 10 to the minus 19th? That doesn't make sense. 2.82 times 10 to the minus 8th, or 9.1 times 10 to the minus 31 kilograms, or 1.1 times 10 to the 30th kilograms. Let's turn the page and we'll see the answer. Then I'll show you how they got that. So the correct answer is 9.1 times 10 to the minus 19th kilograms. Get my little pin out. Okay, so the charge is 1.76 times 10 to the 11th coulombs per 1 kilogram, right? Now we're trying to find kilograms. All right, so what I'm going to do is take the inverse of that because I want kilograms. So I've got 1 kilograms, right, over 1.76 times 10 to the 11th coulombs. All right, so now if I multiply let's see, 1.6 times 10 to the minus 19th coulombs, right? And this is dimensional analysis. I can cancel out my coulombs, and that's going to leave me kilograms. So let me get my trusty calculator out here in just a sec. And I'll show you the calculation I did. So I've got my trusty calculator out. So if I have 1.6 times 10 to the minus 19th, okay, and then I'm going to divide by 1.76 times 10 to the 11th, I get well, no, I didn't do a math calculation right. All right, I put a negative instead of the minus. So what I got was what? 9.1 times 10 to the minus 31st kilograms. So what does that tell me? That tells me that the mass of a electron is very, very, very small. So which of these would be the charge, could be the charge of a drop in the Millikan oil experiment? Okay. Take a break, take a second, and we'll find out. Well, I hope you've had time to think about that, because if you think about it, that 8, because if you take 8 divided by 1.6, that comes up to, we've got a little pin going in. There it is. A little pin going in and advance forward. That comes up into 5. So that would be the answer, number C. All right, 8. There we go. 8 times 10 to the minus 19th. That's the only one that makes sense. So that would be like 5 electrons. All right, so the magnitude of the charge on an electron was determined by what? The magnitude of the charge, of course, it was determined by the Millikan oil drop experiment. So now we know the mass of the electron. We could calculate that. And we also know the charge of the electron, because Millikan found out what the charge of the electron was, and because we knew the charge to mass ratio, we could calculate the mass. So we got the electron discovered. Now, after the discovery of the electron, scientists believe that there must also be a positively charged particle in the atom. So to look for these, they used an anode ray tube. All right, so they had the positive anode going to the cathode, the negative side, right? So they shoot electricity in there, and they put holes in the cathode so that the particles could move through it. All right, and the positive charged particles would be attracted to the cathode, the negative, anode, or node, if you would. They did find that the particles were indeed moving from the anode, the positive charge pole, to the cathode, the negatively charged one. So since they move toward the negative plate, they must also be negative. So the anode rays, they called those protons, and these were found to be much heavier than electrons. Like one proton was 1,840 times the mass of an electron. So the heaviest anode rays in oxygen were found to be 8 times heavier than those in hydrogen. It was assumed that oxygen had 8 protons compared to hydrogen's 1. So the number of protons an atom has is different for each element in the periodic table. So what can we say about protons? They were originally called cathode rays. They move faster than cathode rays. They have a larger mass than electrons, or they move from the cathode to the anode. Of course, the correct answer has to be they have a larger mass than electrons. So, which of the following is not true regarding protons and electrons? Both were found in all atoms. Their charges are equal in magnitude. Well, they are. Our protons are significantly heavier than electrons. That's true. All elements have the same number of protons. We know, of course, that is not true. So, the mass of an electron was found to be 9.1 times 10 to the minus 31st kilogram. All right. So, what is the mass of a proton? So we've got that. We determined the mass of the electron, and we know that one proton is 1,840 times the mass of an electron. So, do my little math on my calculator. So I'm going to do 1840 times 9.1 times 10 to the minus 31. I come up with a 1.67 times 10 to the minus 27 kilograms. So, guys, those are electrons and protons. And these were all discovered around the turn of the century, of the 19th century, in the late 1800s. So it's only been about 130 years or so that we found these two subatomic particles. So anyway, we'll talk more about the neutrons and the nucleus and such on our next little video. So this is Coach Scott saying, guys, have a great day.